about ready. 1 minute. Precise.
Well, good morning, everybody. Our speaker is Dr. Jeff Mills. He is associate professor from University of Cincinnati, and his talk is about probabilistic biostatistics adventures with Julia from code to clinic. Welcome.
Yeah, I shortened the title for so I could get it all on. This is joint work with Jeff Strong, who's a psychiatrist at the University of Cincinnati and Cincinnati Children's Hospital. I'm not really a biostatistician. I'm kind of a fake one. I'm an econometrician, and I got working on this because I met Jeff Strong, and we got talking, and he does clinical research and runs clinical trials. I don't know if you saw the Pfizer talk yesterday. They did all that really cool stuff, and it was really fascinating. And then he had that little bar graph, and right at the end, the least satisfied group with a statistical analysis. Well, that's my neck of the woods. So I'm trying to change that. I'm trying to make that interesting and do all the same cool stuff that they did before. You know, they get to the end, and then especially for FDA approval and stuff, you have to use, you hit proc mixed and get a p-value. If it's less than 0.05, good. Otherwise, no wonder they're dissatisfied. It's boring, and it's the same thing we've been doing since the 1930s or before, and we know better. So I posted all my stuff. Well, most of it's on there, not all of it. It will be by the end of the week, but on GitHub, if you're at all interested. Oops. So let's get to the talk proper. If I can stop misclicking. What am I doing wrong here? I think how do I make that full screen? What do I have to do? It was? Oh, okay. It's different on here, sorry. So thanks to Young Family Foundation and Taft Research Foundation for research support. Thanks to JuliaCon organizers for the opportunity to present, and lots of colleagues, co-workers involved. Can't list them all, we don't have that much time. So what is probabilistic statistics? You take a statistics class, right? There's two sections. There's probability theory, then statistics, and there's like that much relationship between the two. So what probabilistic statistics is, in the easy way to say it, is you take the second half of the book and you throw it away, and you just stay with the first half. You apply the probability theory, right? So there's this work done in, there's a Cox in the 60s, and James did a lot of work on this, applying the idea of probabilistic logic, right? So instead of deductive logic, if A then B is true, it's if A then B is more plausible, right? So I learn A, that tells me something about B, but I don't know B is true for sure, but it makes it more likely, more plausible, right? So the definition of probability is then degree of plausibility. And so you can apply this to any proposition, right? So pretty much anything. Given the available information, what's the degree of plausibility? All probabilities, there's a famous DeFinetti's book starts with a big capital letters. There's no such thing as a probability. What he really means by that is all probabilities are conditional. There's no objective probability of A. You have to know something about A, right? So probability of B given A, given what you know, the information said A, is degree of plausibility somewhere between 0 and 1 and so on, okay? So we want to apply that probabilistic logic to statistics. So we've got these conditional probabilities, probability of B if A is true, how plausible is B? B is often something that's not random nor a variable. More often than not, it's a constant when we're doing statistics. So we're interested in these degrees of plausibility about propositions when we're faced with incomplete information or uncertainty, right? So it's the application of that. So we skip all the statistics in the second half of the course and just apply probability theory. Ed James' book is a great place for reading about that. So simplest case is, obviously S successes in N trials, right? So you have some outcomes, success or failure, and there's some unknown probability of success, right? Common misunderstanding in the literature. It's even Wikipedia is wrong on this, which, you know, is kind of horrifying that Wikipedia could be wrong about anything, but maybe I'm wrong then, I don't know. But theta's a constant, it's not a random variable, right? It could be a universal constant. In this case, it's a probability of success, right? Like a dice roll or flipping a coin. It's not a random variable, and Bayesian inference doesn't assume it's random, okay? Really, all it is we're having a probability distribution about our uncertain knowledge of that constant, okay? So it's a probabilistic representation, okay? Degrees of plausibility. So for example, you know, if I set theta equal to some number, 0.3, and I set the seed, I wanted to set the seed to 42 to be really cool, but it gave me exactly 0.3 when I generated 10 numbers, and I didn't want that, so I had to make it 41. And then we generate some random numbers. Well, if we know all the information other than theta, right? So if I don't tell you theta, but you know exactly the random number generator algorithm I'm using, and you know the seed, then you need more than one observation because there's more than one values of theta that'll give you ones or zeros for the first few trials. So you need more than one observation, but you can exactly determine theta pretty quickly, right? But if you don't have that, if all you have is the sample, right, so the 10 observations, then we have to start representing our uncertain knowledge probabilistically. So that's the idea, right? So here's that simple case, right? So I generate some data, give you the data and nothing else, and you know that it's some Bernoulli process. You just get a bunch of ones and zeros, and you're trying to learn about theta. You don't know the true theta is 0.3. If you only have 10 observations, you're on that blue, really wide line there. You're pretty darn uncertain about theta. It's somewhere between 0 and about 0.6. And then as you get more information, you get more and more precise knowledge about theta, right? So theta is not a random variable, but your knowledge about it is probabilistic, okay? So that's the idea. So there was this guy, so, you know, from the axioms, simple axioms of probability, you get the Bayes theorem really fast, okay? That's one of the first things you do in probability theory, and then most of those courses forget about it from then on. But if you use Bayes theory as a rule, call it Bayes' rule for inference, then it's really cool, except you run into these analytical intractability problems because you've got to do lots of integration, and it becomes multidimensional. You run into the curse of dimensionality. Well, there's this famous mathematician, Stan Ullum, who was in hospital trying to convalesce, and he was playing solitaire. And as a mathematician, he saw that as a combinatorial problem. What's the chance of getting a success where you can actually lay down all the cards when you shuffle? And found it was just very difficult, and he couldn't solve it. So he just realized, well, I can just count, just keep playing and count how many successes. And you rush back to Los Alamos, you know, one of the few places you could actually use a computer back then, and invented Monte Carlo methods. And that's where Monte Carlo simulation and metropolis methods were first used and discovered and published in some chemistry journals. So statisticians knew nothing about it, and statisticians didn't have computers. So it took us another 50 years to realize we could use this stuff for probabilistic reasoning. So that's, you know, it was really the 1990s. Markov chain Monte Carlo methods became widespread, started to be used. And we can actually avoid the curse of dimensionality by doing that. So we got this unknown fixed quantity, call it theta or whatever you like, which we're interested in. And we have insufficient information to know exactly what it is. So we want to make probabilistic statements about it. So the application I'm looking at is biostatistics. So now we've gone from probabilistic statistics to biostatistics. So we're analyzing randomized controlled trials, right? So you've got S successfully treated out of N patients with some unknown probability of success. That's simplifying it in many ways, but let's keep it simple for the sake of the talk. So there's some underlying probability. What the clinician wants to know is when somebody walks in my door, what's the probability if I give them this treatment, it's going to work? They're going to feel better, right, in a couple of months, a week, whatever. And then with quantitative data, we're more interested in average treatment effect. How much are they going to get better? If we can quantify that, how much will they improve? How much will the symptoms reduce? We can also look at side effects. You know, what's the chance they're going to get a side effect? How bad will they be? Those kind of things. And then really we'd like to combine the evidence from randomized controlled trials. A lot of these trials are pretty small, right? So you've got 30, 60 observations, but maybe there's 5 different trials. If you can combine all that data, that makes one big trial, okay? And obviously there's a lot of interest nowadays in using the evidence that's available in medical records. So it's not controlled, but there's a lot of data, so maybe we can learn from that. Well, we know we can. So the problem you run into is this two-field or two-hat problem, right, where you have to wear more than one hat. So you've got your clinical statistician, that's Jeff Strawn. He's a psychiatrist. I know, so, you know, he's the bio in biostatistics. I know very little about biology even at all. Most of it I've learned in the last few years. I'm the statistics side of it. So we're fortunate because we got 2 people, right? So he wears the clinical scientist hat, and he was wearing both of these hats and pretty unsatisfied because, you know, you do all this really cool stuff, come up with this data. It takes 5 years to run your clinical trial. It costs a lot of money. And then you put the data into SAS, run proc mixed, and get the p-value, and it's either 0.51 and you're depressed, or it's 0.049 and success, you publish, right? So and he wasn't very happy with that. So that's I got chatting to him, and he knows enough about statistics that it's dangerous, right? That I can fool him into letting me use all these Bayesian methods and probabilistic reasoning. I mean, really, I'm cheating here, right? Because the second hat, really the first hat as well, but the second hat is more than one person, right? I've got a statistical program. Well, that's a statistician and a programmer. I'm more of a statistician than I'm a programmer. Really, you need a statistician and a computer scientist, so you're wearing multiple hats there too. So what you want is, you know, it's too expensive and too difficult to get all these people together in the same room for 5 years and do it all the way, ideally, in a utopian world you would. So something's got to give, you've got to compromise, and I think Julia allows us to do that. We can set up more complicated methods than just looking at the p-value, do something more interesting, and make it pretty user-friendly. So that's sort of the goal. Okay, so we're going to use the Bayesian, Markov chain, Monte Carlo machinery plus Julia, and end up with something that's sophisticatedly simple. Okay? So we can do exact small sample inference. We're not using p-values. We're actually calculating probabilities that theta is some value. We can analyze pretty complex problems just using very basic concepts. Once you've got your Markov chain, then you're just doing frequency distributions, density plots, means and medians, standard deviations, most of the kind of things you learn in intro statistics. A couple of other bells and whistles are all you need. Okay, so my side interest is overthrowing p-values, what I call 5% itis. You know, that's sort of the ox-drawn plow for me. We did that back in the 30s, or so I wasn't around in the 30s even. I'm not quite that old. You know, we've had a lot of advances in statistical methods, computing power, computational statistics, so we can do better than the p-value. The statistics literature is throwing its hands up and wringing its hands and tearing its hair out over p-values, but it's not filtering down because there's, you know, we need a sensible alternative. So that's part of the idea from mine. There's a really strong institutional inertia and bias in this. You know, you have to have your 5% significance. The editors and referees need to learn about this. So it's a bit like the QWERTY keyboard. We all use this horrible keyboard that's designed to slow you down and give you carpal tunnel because, you know, you had those horrible typewriters with the curve. We can do much better, but nobody does because we're stuck with this thing, right? So what you need is a bridge. You need to be able to give you if you could give people 2 keyboards and somehow they could seamlessly switch between them or use them both at the same time, it'd be easier. So that's the idea, is to still report p-values, but give them something else that makes sense as well. And of course, visualization, okay? Picture paints 1,000 statistics. That's really my talk from last year, so you can take a look at that. So randomized controlled trials, very expensive. We want to improve the methods. So here's an example. It's the child-adolescent multimodal study. There were over 400 participants. They were randomized to 3 different treatments and a placebo, so SSRI, is a selective serotonin reuptake inhibitor, sertraline, and then cognitive behavioral therapy, and then both of those, and then the people who got the placebo. And there was only, 1 in 7 got the placebo, 2 out of 7 got each of these to try and reduce the number of people getting the placebo. There's different measures. It's very difficult to measure anxiety. You have the child do a survey, the parents, the psychiatrists, to try and measure how somebody's feeling and what they're anxious about and what kind of anxiety. And then there's rating scales, different kinds. There's a quantitative one, the categorical rating scale. So we can look at all those things. So if we just use some pretty simple probability theory, Bayes' rule, we can update. We can say, okay, start with, I don't know what theta is, the chance of success, uninformative, right? That's a beta 1,1, that's a uniform distribution. If I have a Bernoulli or binomial likelihood, then that gives me a beta posterior distribution, and all I need is S and N, number of successes and N trials. So I can draw a lot of draws from that distribution, pseudo-random draws, given S and N, my values of theta, and plot these distributions and do whatever you like with them. But then the neat thing is I can take the difference of those draws, those random draws, and that gives me the posterior distribution of the difference, okay, which is the Behrens-Fisher problem. There's all kinds of assumptions you have to make to do that analytically. It gets kind of messy. And better than that, I can take the difference of the difference, right? So if I've got 2 treatments, treatment minus placebo, and I want to compare those, that's a difference of a difference. And that's analytically intractable, and you have to make an awful lot of assumptions to do something with that without doing this method. But if you just use MCMC, or just in this case, I'm just using Monte Carlo, I'm just drawing from the posterior, the beta posterior for each of the treatment and the placebo, and then you take in differences of those draws, and the rest is basic statistics. So in place of the p-value, we can compute posterior odds, which is essentially the height of the density at whatever the value in the null is, and the mode of the posterior, so the maximum posterior estimate. Okay, so this gives, actually it's not really a p-value, I cheat, it's a Bayesian p-value, it's the area in the tail. So instead of shifting the distribution to the null hypothesis 0 and looking at areas in both tails, I'm just computing the area in the tail of the posterior to one side is 0. Why would you look in the other tail? Beats me. And there's in these cases, there's a 1-to-1 correspondence between the posterior odds and the p-value. So the odds are, almost 16 to 1 against the null hypothesis here. That corresponds to a p-value about a 0.02 and so on. So then another application, another thing we can do is updating, right? If you conduct a randomized trial, you've got to decide, am I going to stop at 100 patients, or am I going to stop when I have 30 successes? Or what's my stopping rule? If you take the Bayesian approach, you don't have to have a stopping rule, and so you can analyze the data as it comes in, or every several patients, right? So as I said, with a binomial or Bernoulli likelihood and uninformative prior, you get this beta posterior distribution. We can update that. It's trivial to update it. Just add the S's together, add the new S values, new number of successes, and new number of observations, excuse me, and you get another beta distribution. So you can see as you go along through the trial, every several patients, what are my results looking like? Should I stop or should I keep going? Okay, so you can tailor the length of the trial to getting the outcome you want without using too many patients. Same thing if you have quantitative data. I won't bore you with all the math, but central limit theorem, maximum entry principle tells you that the mean is a very strong justification for the mean being normally distributed. You can use that with an uninformative normal gamma prior, and it's all the same kind of thing. You can use MCMC if you prefer to. Thought I'd better give you code instead of equations. So here's a simple function to do that for the mean. Update the mean. You just give it, since the mean, the standard deviation and number of observations is sufficient statistics for a normal distribution, or for a t distribution you don't even need the number of observations for a normal. So you can update all and end up with a new mean, a new standard deviation, and a new number of observations, combining 2 sets of data like that, so as you get more observations. So here's what happens when you do that, right? So you start with a few observations. So when there's 18, you get posterior odds of only 1.4 to 1 against the null hypothesis, p-value of 0.76. And as you get more and more data, you get to about 70 or so observations, and you already got a really small p-value. Your odds are already over 64 to 1. So in this case, we could have stopped the trial a lot sooner, right? I mean, you don't need to go to 198 observations and have 30,600 to 1 odds against or a p-value incredibly small. You can just decide when you've got to be a little careful. You can't just say, okay, 5%, because then you're going to get a bias in your stopping rule. So you want to go beyond that. But you certainly don't have to go all the way to, we're not trying to detect gravitational waves here. We're trying to cure patients, so let's not give too many placebos. Here's the same picture in a static form, right? So you start with the wide blue line. I don't know if you can even see that on that, but it just gets sharper and sharper, right? So you can pick a more sensible stopping rule, and the trial can be stopped when everybody's decided that, when the internal review board, institutional review board, et cetera, said, okay, you've got successful results. Let's not torture any more patients to prove what you've already shown. Another thing we're working on is Bayesian hierarchical models, applying that to meta-analysis, so combining trials. So you've got results from 4 or 5 different trials. You want to combine them. We can just use Bayesian updating, same as we just did, same formulas. Give me the S and N's or the means and update. But that's assuming all these trials are exactly the same. Right? I'm exchanging patients from one trial to the other and treating them all as one big trial, but there's a lot of heterogeneity in trials. Different people conducting the trials, different locations, maybe different doses, maybe slightly different medications, but in the same class. So you want to allow for that heterogeneity, so that's what the Bayesian hierarchical model does. So here's sort of the Bayesian hierarchical setup. If you start on the third line, all the little distributions, that would be sort of Bayesian updating, would just be combining those and getting one distribution at the end for those, and all the rest is just taking differences. But then we can go a couple of steps up and have distributions on these parameters. So the idea is theta for each trial, each independent study is a little different, but they're all from some distribution, some overall distribution, and that's what we're interested in. So to do that, I really like the package Turing. It's very nice for this kind of stuff. You can do all kinds of Hamiltonian Monte Carlo, then no U-turn sampler, and so on. And as you can see, it's very easy to specify. So on your right is what I use to generate the results you're going to see, because that turns out to be a little more intuitively understandable if that's exactly what you're doing. So you get this distribution W, which is the overall distribution of theta. On the left is just a different specification, which is really more useful when you have covariates. You want to make your model a little bit more complicated, you start putting in covariates. But you can see they're very simple setup. Here's the results of an examination of side effects. So there are 5 randomized controlled trials, and we're looking at the side effect activation, which is, think of it as sort of agitation, mental hyperactivity, if you like. So it's a side effect that occurs. So here's the distribution for the 5 different trials, and then W's the hierarchical distribution, sort of averaging over the 5 trials and taking into account the heterogeneity. This is the kind of output you get from Turing. More numbers, you can always look at those at your leisure. Here's the difference on the right between allowing for heterogeneity and just doing the Bayesian updating. So you can see there's more uncertainty because we're allowing for differences in the trials. Okay, but you can see that 0 is nowhere near that distribution. Got a pretty strong result. Here's updating over weeks. So these trials are conducted. So the distribution on your left here is at baseline, week 0, right? Every effect is essentially very close to 0, as it should be. And then as the weeks go out, you get a stronger effect. And then the plot on the right is just those distributions. So week 0, week 2, 4, 6, and 8 from those. So key advantage of Julia in all this for me is exactly this. I can focus on the problem, right? Not trying to figure out how to write code in a couple of different languages. I'm not a computer scientist. My code is horrible. My examples on GitHub are pretty short, so hopefully it's not too horrible, but you know, I try and write better code, but I'm not that good at it really. You know, but for me, the code is the means to the end, and most of my code is often one use, so it doesn't have to be that great. But Julia is great for, it actually forces me to write pretty decent code, and it's fun, and you can focus on the problem. There's lots of other examples from our research. Take a look at that if you're interested, or talk to me. There's also the package, I talked about that last year, Bayes testing for doing the hypothesis testing. Thank you.
Okay, does anybody have questions? Yes, if you want to come up here.
What do you use for plotting? They're very pretty plots.
Plots.
Your plots in your talk.
Plots.
Oh, you use plots.
.jl.
Okay. Yeah, they're beautiful.
First plot takes
All right.
1,000 years to load, of course, but
Yeah,
after
but-
that, it's a utopia. You know.
So I had an actual somewhat statistical question, which is why is it kosher to decide when to stop? I mean, don't you have the same danger of being like, well, it looks good right now, so we're going to stop now?
Yeah, I mean, you have to, but you can do that dynamically, right? You don't have to decide before you've even run the trial, we're going to stop at 100 patients. You can, and you have a review board, and you don't, like you say, you don't want to stop at 5% because it could move back, right? You could get more patients and end up at 10% significant or whatever. But you know, you can look at different possible stopping rules and take that into. I mean, there's no clear answer to that anyway, right? 5% is very arbitrary,
Right.
and only applicable in.
But if you get down to 0.0001%, then there's
Yeah.
no point in continuing, and that's okay.
Exactly. Yeah.
Okay. Thank you.
So I have a question. If you've looked at this at all with things like large genetic cohorts where it's not as bad as 0.05, it's that plus Bonferroni correction for like, you know, 10,000 SNPs or something.
Mm-hmm.
So you have your actual p-value that publishers require is like, you know, 10 to the -6 or whatever, because you're doing Bonferroni correction to account for all of those multiple tests. So is this a way to potentially improve that and increase power?
Yeah, actually, that's a big advantage of the Bayesian approach is you can, if you do it properly, you can avoid the whole need for Bonferroni corrections because the updating will take that into account. So, you know, you do all the tests, the multiple testing, and at the end, it's 5% adjusted automatically for all that. So it's actually a big advantage of the Bayesian approach.
In the process you're doing, do you need placebos? Because essentially you're extracting signal from noise.
That's always my question. Yeah, when I talk to, you know, Jeff's the bio, I'm the statistician, but I guess, you know, to do these trials, you've got to report your 0.05. You've got to have some placebos. You know, I think we could move beyond that and use the same placebo group. The argument is heterogeneity again, but if we can model the heterogeneity, then we can use a placebo group from somewhere else, right? So the idea with the randomized controlled trial is we've got exactly the same setting, right? So we've got this group in the same setting, not getting the treatment, and this group getting the treatment. So
But is
plenty
it
of-
ethical not to give people the
Well,
treatment?
yeah, that's the whole issue, right?
Yeah.
I agree.
All right, if you
Thank
don't
you.
have, actually, we got like 30 seconds. You can finish in 30 seconds?
Yeah.
Okay.
I can only make a remark then.
Okay.
So regarding your question and your answer, I think that the clue is that you report p-value, but it's not a frequent p-value, but
It's not really
Bayesian
a
p-value.
Yeah.
And actually, you could correct this p-value because in Bayesian, conditional on the stopping rule you have,
Right.
which is not easily possible in frequent setting.
Right.
Yeah, it's not really a p-value. I'm cheating. You're right. It's a Bayesian probability. Thank you.
All right. Thank you so much. If you have any questions, you can ask after sessions. Thank you.